Hello everyone. So we are coming to the fifth module of our course, Fluid Mechanics and Machinery. And the fifth module deals with impact of jet, followed by different types of turbines, that is impulse and reaction turbines. So before we go into the details or the solve problems based on the turbines, we should have a thorough knowledge on the impact of jet. Impact of jet is nothing but the we are trying to find out the force exerted by a jet on a plate, which may be stationary or either it may be moving. So as I told earlier, before solving the problems related to turbines or before understanding the various mechanisms of various turbines, we should understand the impact of jets on a plate. So basically, our this topic, that is impact of jet, can be broadly be divided into two. That is impact of jet on a stationary plate and a moving plate. So what do you mean by a impact? Impact of jet means here we are trying to find out the force exerted by the jet on a plate, and that itself is categorized into two: stationary plate or moving plate. So for this study, in the entire topic, our derivations and our study will be based on the Newton's second law of motion, or which is more commonly known as impulse momentum equation. So as I told earlier, we have divided it into two parts. First is a stationary plate and then the moving plate. Each of these is again divided into three categories. That is, stationary plate is again divided into, the plate can be the stationary plate can be vertical to the jet, plate can be inclined to the jet, and the plate can be curved. Same categorization follows in moving plate. So in this video session, we will first look into stationary plate, and in another video section, we will look into detail the moving plate. So now let's look into the first case, that is force exerted by the jet on a stationary vertical plate. So as you can see here, a pipe through which flow is taking place, and at the end of the pipe a nozzle is fitted, and from the nozzle water is getting or liquid is getting ejected, and here is a stationary plate. The plate is fixed, and the water strikes it, and water is being deflected in both of this direction like this. So let v be the velocity of the jet, d is the diameter of the jet, and a is the cross section of the jet. So the area will be pi by 4 d square. So as I told earlier, impact of jet means we are trying to find out the force exerted, and is based on the Newton's second law of motion or impulse momentum equation. So as you can see, force exerted by jet on the plate in the direction of the jet. Here you should clearly understand the word in the direction of the jet. That is, this is the direction of the jet. So if you can assume like this is x direction and this is y direction. So direction of the jet is in the x direction though. So we write Fx is equal to Fx, that is force exerted, is as per the Newton's second law of motion, is rate of change of momentum in the direction of the force. That you can write initial momentum minus final momentum by time. So momentum is nothing but mass into velocity. So mass into initial velocity minus mass into final velocity by time. So you can write it like this: mass by time into initial velocity minus final velocity. So mass per second, mass by time means mass per second. We are considering it per second. So mass per second into initial velocity means the velocity of the jet before striking. So this is the stationary plate, and the jet of water before the striking the plate, what is the velocity? That is the velocity of jet before striking. So as we have mentioned here earlier, the velocity of the jet before striking, or the velocity of the jet, is v. Now, and the final velocity of jet after striking. So after striking, you can see that the jet is getting deflected in two directions. In the or in other sense, in the vertical direction only. There is no motion of jet in the x direction after striking the after striking the fixed plate. That is why here we have substituted 0. Hope you have understood. So simplifying, we will get rho a v square. So this is the expression for force exerted by the jet on the plate in the direction of jet, rho a v square. So if you have clearly noted one thing in this derivation, we have taken here force exerted Fx is equal to initial momentum minus final momentum. So why didn't we take final minus initial? Okay, the answer is the if we are finding the force exerted on the jet, then we will consider final momentum minus initial momentum. Okay, I repeat, that is if you are considering force exerted on the jet, here we have considered by the jet. So if you are considering if you are finding force exerted on the jet, then we will have to consider Fx is equal to final momentum minus initial momentum, or final velocity minus initial velocity. But here, as we are considering, or we are more interested on the force exerted by the jet on the plate, on the stationary plate. So in that case, we have considered initial momentum or initial velocity minus final velocity. And again, another thing to notice, the velocity, the value of the density here, rho, will be in SI unit. So that will be kg per meter cube. Force Fx will be in Newton, and value of rho, that is density of water, is 100 kg per meter cube. All these things you will better understand when you solve the problem. Now moving on to the second case, that is again the stationary plate, but the here stationary plate is inclined flat plate. So again we will consider the same thing, that is a pipe having a nozzle and water is hitting here, and here the plate is stationary but the plate is kept at an angle. And so here the plate is say at an angle theta with that of the direction of jet. So we, as in the earlier case, we defined v is the velocity of the jet in the direction of x, theta is the angle between jet and plate, and a is the area of cross section between area of cross section of the jet. Now we can write mass of the water per second striking the plate is rho av. So how did we get that equation? That is, we know that rho is equal to mass by volume, or in the other case, in other words, m is equal to rho into v. Rho into v. V is the volume. So here we have mass of water per second, that is mass per time. So that will be anything per time, we commonly denote it by m dot, a dot on the top. So m dot mass per time. So which means density into volume, I can write area into another dimension, let it be length or any other length. So a into L will give you the volume. So we are writing m dot, that is mass per time. So rho into a into L by t per time. So what is this L by t, or any dimension per time, is nothing but the velocity. So I can write rho into a into velocity v. So that is m dot or m by time. So hope you understood. So in the derivations to follow, we will be directly writing mass of water per second is equal to rho av. So you should understand how you get this expression rho av. Here a into v is nothing, is not, v is not volume, v is the velocity of the jet. Now here we have taken Fn, that is, what is n? Mass of jet striking per second in the direction of n. So n is this normal direction. This is the direction in which jet is flowing, and this is the normal direction. So if this angle is theta, this is 90 minus theta. So this is Fn, and we can divide it into two components, that is V sin theta and V cos theta. So force exerted in the direction of n is mass of jet striking per second into initial velocity before striking in the direction of n minus final velocity in the direction of n. So I can write mass of jet striking per second is rho av, that we substitute rho av into initial velocity of jet before striking in the direction of n. So before striking in the direction of n is, and final velocity, as you can see here, after striking there is no component in the direction of n. So we can substitute here 0. So the final expression Fn is equal to rho a v square sin theta. Now this Fn, or the normal component, can be resolved into two components, that is one in the direction of the jet and other perpendicular to the direction of flow. So we name it like Fx and Fy. Fx is component of Fn in the direction of flow, that is Fn cos 90 minus theta. So substituting the values, Fn cos 90 minus theta is sin theta. So Fn is rho a v square sin theta into again this sin theta. So rho a v square sin square theta. Similarly Fy, and we get the expression rho a v square sin theta cos theta. So now coming to the third case in the stationary plate. So the third case, as it was mentioned earlier, it is the plate is curved in shape. So again, this third case is again divided into three subcases. That is, this jet of water can be striking at the center or tangential to the curved plate. So as the first case, we will consider that the force is exerted by the jet on a curved plate, and the impact of jet is at the center of the curved plate. That is our first case. So let us consider a jet of water which strikes a fixed curved plate. This is a fixed curved plate at the center of this plate. The jet, after striking the plate, comes out with the same velocity. Why? Because this we are throughout this derivation we are assuming that the plate is smooth. This curved plate is smooth, and what we mean by smooth curved plate means there is no loss of energy due to impact of the jet. That is, jet after it is hitting the curved plate will move through this tangential direction as shown in this figure through both up and down directions. So in all this derivation, you should understand that we are assuming the plates to be smooth, so that there is no loss due to the impact. Losses are negligible. And so after hitting this curved plate, we can see that it is getting separated like this, and we can resolve it into two components. If this is theta, this is v cos theta, and this is v sin theta. So in the direction of the jet we have v cos theta, and perpendicular to the direction of the jet we have v sin theta. So we can write component of velocity in the direction of jet is minus v cos theta. So why this minus means, we know that the direction of the jet before striking is like this, but as you can see, after striking the velocity is getting, the direction of the velocity is getting reversed as shown in this figure. So we can say that this is minus v cos theta. Hence we are writing here component of velocity in the direction of the jet is minus v cos theta. And similarly, component of velocity perpendicular to jet is v cos theta. We take this as a positive direction, so we can say that it is v sin theta. Now, as always, force exerted by jet in the direction of jet is Fx is equal to mass per time or mass per second into V1x minus V2x. What is this 1x and 2x? V1x means 1 means initial velocity and x means in the x direction. Similarly, V2x, in the 2 means 2, it is final velocity, and x means again in the x direction. So V1x is initial velocity, that is before striking the jet is having velocity v. So initial velocity in the direction of jet is v, and V2x final velocity we know that in the direction of x direction, in this x direction, the component of velocity is minus v cos theta. So we substitute minus v cos theta. Substituting the values, fx is equal to rho a v. In last derivation, previous derivation, I have already mentioned how we got this rho a v, density into area into this v is velocity, into v1x is v minus v cos theta. So minus minus becomes plus, and finally we will get the answer fx is equal to rho a v square into 1 plus cos theta. Similarly, we will have a component fy in the perpendicular direction. That also we can write it like this. And similarly, when substituting these values, we'll finally get the answer fy is equal to minus rho a v square into sine theta. Now coming to the second case of the curved plate. Here we are assuming that the jet of water is striking the curved plate at one end tangentially and the plate is symmetrical. So as you can see in this figure, this curved plate is symmetrical about this through this horizontal axis, but here the jet of water is not striking at the center. Instead, it is striking at one end tangentially. So here also the curved plate is smooth, and the angle made by the tangents at two ends of the plates will be the same. That is, we have initially the jet is striking here, and we have an inlet angles as well as the jet leaving here. So we will have outlet angles. So as the plate is symmetrical, we can say that both of these angles will be the same. Next, in the in the next section, we have unsymmetrical case. There we will explain more about the difference in angles. So here again, let V be the velocity of water. Theta is the angle made by the jet with x-axis the inlet of the tip of the curved plate. And you can say you can assume the plate to be smooth and there will be no losses. So coming to our derivation, Fx is equal to mass per second into V1x minus V2x. So rho AV into initially itself the velocity is having a component V cos theta. In the earlier cases, the jet velocity was v because it was going in the straight direction in the direction of x. But in this case, it is hitting tangentially, so the velocity is v. But in the direction of x direction, we have to take the component. So the initial velocity, that is velocity before striking, will be v cos theta. And after striking, the final velocity will be again v cos theta, but in the negative direction. So we have denoted it as minus v cos theta. Finally, we will get the answer like this. And similarly, we will have a component fy, and substituting the values, we will get the answer. Fy component will be 0 in the case of curved plate, curved symmetrical plate, when the jet of water is striking at one end tangentially. Now we come to the last case, that is here. Again, the plate is stationary curved plate, and the jet of stream is striking at one end tangentially. But here, the difference is that the plate is not symmetrical. The plate is not symmetrical about the x-axis, or rather the plate is unsymmetrical. So what even though the figure is same, there is a minor change here. That is, the inlet velocity angles will be different from that of the outlet velocity angle. So you can say that if theta is the angle made by the tangent at inlet tip with the x-axis, so this is theta, this angle is theta, and phi is the angle made by a tangent at outlet tip with the axis. So this you have to correct. This is phi. This angle is phi. Therefore, this component will naturally be v cos phi, and this will be v sine phi. There is a minor correction like this. So again, v1x, v2x, we can write it like this. It is the same way as that discussed earlier, so I am not going to repeat it. And when substituting first fx, you will get the value of fx as rho a v square into cos theta plus cos phi. And here fy is not 0, so we will get the answer like fy is equal to rho a v square sine theta into sine phi. So these are the different cases of stationary fixed plate. So in jet of uh, impact of jet, we have discussed only the stationary cases, that is the plate is stationary, and different cases related to the stationary plate, that is first we have considered uh, the vertical stationary plate. Then the plate was inclined. Then the plate was curved. In the curved case itself, there was three sub cases: hitting the curved plate at the center, then hitting the curved plate at one end tangentially, and the plate was symmetrical. And again, last case that we have discussed just now, hitting the curved plate tangentially, but the plate is unsymmetrical. So now we will look at some of the numerical related to this stationary fixed plates. So as a first question, water is flowing through a pipe uh, at the end of which a nozzle is fitted. The diameter of the nozzle is 100 mm, and the head of the water at the center of the nozzle is 100 meter. Find the force exerted by the jet on fixed vertical plate. The coefficient of velocity given is 0.95. So as you can make out from this question, this is a case of fixed vertical plate. That is our first case. So recall that our equation of force exerted was rho a v square, rho into area into capital V square, where rho is the density, a is the cross sectional area, and v is the velocity. So given things, diameter of the nozzle is given 0.1 meter, head of the water capital H 100 meter, coefficient of velocity we denote it by CV 0.95. So we can first find out the area of the nozzle. So in this equation we have to find out area. So area is equal to pi by 4 into 0.1 square. Similarly, we have to find out the velocity. So finding out the velocity, we have an equation v theoretical velocity of water. This equation you might already be knowing. This is equation from the pitot tube. Uh, so v is equal to root of 2gh. So root of 2 into this is the theoretical velocity. But in this question we are given a coefficient of velocity. So to get the actual velocity, we have to multiply this v theoretical with that of cv to get the actual velocity. So if you are given in the question a coefficient of velocity, you have to consider that and find out the actual velocity. So this will be our value of v. So then substituting the equation f is equal to rho a v square, substituting the values, we will get the final answer as 13.9 kilonewton. So that is the force exerted by a jet of water on the fixed vertical plate. Now let us look at another problem. A jet of water of diameter 50 mm strikes a fixed plate in such a way that angle between the plate and the jet is 30°. So since the angle is given, this is a case of inclined stationary plate. Force exerted in the direction of the jet is 1471.5 Newton. Determine the rate of flow of water. So here in this case, the force exerted is already given, and you are asked to find out the rate of flow. Or the discharge Q is what is asked. So again, noting down the given things, diameter D is given. You can find the area, and the angle of inclination of the inclined plate theta is 30°. So force in the direction of the jet, that is Fx, is already given 1471.5 Newton. So we already know that for inclined plate, the equation for Fx is rho a v square sine square theta. So as the force is already given, we can substitute this, and from this equation the only unknown is v square. So from this we will get the value of v square as 150 by 0.05, that is 3000, or v is equal to 54.77 meter per second, that is square root of this 3000. And once you have got the value of v, you can easily find out q, that is q is equal to av And finally you will get the answer of Q as 0.1075 meter cube per second, or converting it to liters per second, 107.5 liters per second. Now we will do one last problem also. A jet of water of diameter 75 mm moving with velocity 30 meter per second strikes a curved fixed plate tangentially at one end at an angle of 30 degree to the horizontal. So this is a problem on the last case, that is it is a curved fixed plate and the jet of water is striking tangentially at one end, and angle is given 30 degree to the horizontal. The jet leaves the plate at an angle of 20 degree to the horizontal. Find the force exerted by jet on the plate in the horizontal and vertical direction. So as you know, the curved plate itself is having three cases, that is striking at the center, striking at one end tangentially, symmetrical case and unsymmetrical case. So here how to make out this is, you are given two angles, that is inlet angle is tangentially at one end at a 30 degree to the horizontal. So inlet you have 30 degree and the jet leaves at the angle of 20 degree. So from that you must make out that it is a case of unsymmetrical curved plate. So solving the problem, diameter is given, you can find out the area, velocity is also given 30 meter per second, and inlet angle made by the jet at the inlet tip, we are denoting it by theta is equal to 30 degree. Similarly at outlet tip we are denoting it by phi is equal to 20 degree. So you are asked to find out the force exerted, so substituting the values you will get the answer as Fx is equal to 7178.2 Newton and Fy is equal to 628.13 Newton. So hope you all have understood this session on the impact of jets on stationary plates.